Okay, so to do this lab where we change the diameter of the cannonball every time we fire it, here's how I would go about it. I'm going to click this link to open the generic form. And let's see, it's diameter versus distance. So as I've pressed everyone to understand, I have made this very formulaic. Diameter versus distance. And I think I would, my goal as your teacher is to be able to read your question and understand pretty much how you're doing the experiment just from reading that. So how does the diameter of a cannonball affect the distance it goes? Let's see. How do I want to put this? How does the diameter of a cannonball affect the distance it travels? I don't know. Goes is fine. Goes each time you fire the cannon. Fire a cannon. Okay, and I want that to not be bold, so I'll select all that. The way I did that was the cursor was here, I held shift, and it grabs everything between wherever the cursor was and wherever the cursor now is. All right, I also want to take off the highlighting, so no highlighting. Yeah. And as you can see, I already got started because if I click on this simulation, we'll click on lab, and then I forget what I think it was 51. I forget what I set the cannon at. So I might end up having to do this again. I forget what I should have recorded what what these values were, but I can start over. It's not a big deal. Just wipe out those. I'll set the, this is the diameter because, right, it says independent variable, and that's going to be right here. So this needs to say diameter. Yeah, that's something in the way of the text there. And then this is distance, we'll just say dist. And so let's see, 0.1. We need air resistance on, and diameter is 0.1. You can see what the diameter is right there. Fire. Might have to zoom out. Use the rangefinder. 39.71. 0.71. And then we'll increase the diameter to 2. Oh, this is touchy. There. And I probably should record really 51 and 20 meters per second. I'll say 51 degrees and 20 meters per second. Yeah, just so that, like I said, I was having that problem because I actually started doing the lab the other night, and I'm now continuing this morning. All right, so the second one, did I get the second one? Here's the third one, 38.4. Didn't record the second one, so let me back up. 39.21. 39.21. Then third one was 38.4. 38.4. And so these numbers that I'm getting will be a little different than yours depending on if you pick this angle and this initial speed. It'll be all different, but the graph will still reveal the same kind of information. 0.4 fire. 37.33. Moving up to 0.5. Fire. 3605. 3605. And moving up to 0.6. 3463. 3463. And fire. So what you're seeing in the trend here is that it's I don't know, that looks pretty linear. We'll see better when we see the graph. 39.09. 33.09. 33.09. Okay. Yeah, if the distances that it's decreasing each time are exactly the same, it's going to be linear. 31.53. 31.53. 0.9. 29.94. 29.94. And finally, we're at 1, and we fire 28.38. 28.38. 28.38. Okay, so let's see. I'd say set the cannon at an angle. Let's see. I might say arbitrary angle of 51 degrees. The reason I say arbitrary is because you can pick any angle you want. It doesn't really matter. But once you set it at that angle, it's got to stay the same all the time. And 20 meters per second as the initial speed. If those settings will stay the same throughout the experiment. You don't have to say that, but nothing stops me. And I also want you to know that. I want you to realize sort of an unspoken truth is that everything needs to stay the same except for the diameter. That's the only way you can really perform an experiment that's believable. If you're going to convince people, you've got to keep everything the same except for that one variable that you're manipulating, which is diameter in this case. All right, so you set the diameter cannonball to the lowest setting, and that's 0.1. All right, so set the diameter of the cannonball to the lowest setting, and in this case, 0.1, and that's got some units, I guess. 0.1 meters, 0.1 m. All right. My keyboard is glitching. Okay. Every now and then my keyboard will just stop responding. Okay, there we go. Oh, all right. It didn't write the M. Okay, there. Now. All right. So set the diameter of the cannonball to the lowest setting, 0.1 m, and fire. Record the distance goes in the data table. Increase the diameter of the cannonball to the next setting in the data table. That would be 0.2. And repeat. All right, so that's basically how you do the whole experiment. And now that we've written our procedure, you can imagine that in real life we'd need like a football field so we can measure the distance. Football field. What, a cannonball. Measuring maybe a meter stick to get those in between distances. Meter stick, protractor. That's to measure the distance. Protractor. That's actually, we should say cannonballs of varying diameters. Right. So if I increase, and I am going to decide to say increase, so I can take away that. If I increase the diameter of the, and I take away blah 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 and write cannonball, then the distance the cannonball will increase linearly because the ball will encounter more air resistance as it increases. And just to be clear on the hypothesis, you know, the world of science wants you to make a prediction. And so by writing, by actually saying what I'm saying here, we are, sticking our neck out to make a prediction. And you shouldn't really care about being right or wrong because honestly, even if you're wrong, you're still proving something. You're just disproving. You should really separate your ego out from this experience. And as far as the because, you could live without putting the because in there. It's just, it's not the end of the world if you leave out the because. I just like to include that because it gives me some insight into why you think that. But anyways, continuing on, diameter is the independent variable and distance is obviously the dependent variable. Constants are going to be, same cannon, same part of the football field, same day, same weather conditions. Let's see. Pretty much you want to keep everything the same. Like if you bought bags of gunpowder, like if you're actually firing a cannon and you bought bags of gunpowder, you'd be better off buying the same, using the same bag of gunpowder for all trials because just changing a bag of gunpowder could, cause you to have gunpowder that's like got more moisture in it, or it was just manufactured different, so it's got a little bit more power. And you would actually see that in your data. Your graph would have a hiccup in it, if you will, that would actually show that. If it mattered, if all gunpowder is made exactly the same, then it wouldn't matter. But the truth is, it's an organic substance, and there's a lot of variables that can creep in. But anyways, I'm going to assume. Actually, I can't really. I'm not sure if I can assume. Until I actually look at the graph. So for the conclusion and sources of error, I'm just going to, let's say it does support my hypothesis. this is just hypothetical because it all depends on what it looks like when I'm done, and I haven't created my graph yet. But the data supported my hypothesis. As I increase the diameter, I guess, what did I say here? I wasn't even thinking about my hypothesis as I was just formulaically filling it in. If I increase the diameter, then the distance will decrease, is what I would want to say. Decrease linearly. So as I increase the diameter, the cannonball traveled a shorter distance. And let's get rid of all this highlighting. Okay, and sources of error, let's just pretend. Pretty much the same sources of error would come into play because this is still us using a cannon. So I could just keep that the same. But basically, the sources of error are factors that got into the experiment that you didn't want to get in, but it's just physically impossible to eliminate them all. So don't ever say that there were no sources of error, just because that would indicate that you lack imagination. I mean, there's always some source of error, even if it's just your ability to measure something accurately. Imagine that you think that you're measuring something accurately, but if somebody gets a giant magnifying glass, they could say, that's not 2 meters, that's 2.01 meters. And then even that could be considered inaccurate if you got an even larger magnifying glass in smaller increments. So even just, the ability to measure something is going to introduce tiny, tiny errors. So I'll add that. Also, it's impossible to always measure with 100% accuracy. So there were some tiny errors there. And to make matters worse, when you start doing calculations and stuff in a science experiment, think about every time you have to drop decimal places, because when you do math, you end up with these huge decimals, and nobody's going to keep all of them. So you end up dropping, a tiny bit, at least a tiny bit of the mathematical value in that. So just being clear, there's always sources of error. It's impossible to have an experiment with no source of error. Okay, so that's how I would do that. And now I will go to making the graph. And I'll try to hurry because I know this video is getting longer. Sheets.google. See how fast I can do this, because you guys need to know this shouldn't take very long. I'm going to swipe across the top. I'm going to resize these columns. A little too skinny. So resize, let's do 50. Better. And I'm going to center horizontally and vertically. And now let me swipe them again and drop that down and say insert chart. And remember, we're essentially done at this point. I mean, all the other customizations and stuff aren't necessary. And in fact, I'll just leave it at that. And that's basically the curve. This tells me a lot. This is not linear, but it's gently curving, such that you could almost argue it's linear. So there you go. I'll just copy this, paste it into my document. Paste and link. And there we go. That's how we do it.